After the kickoff yesterday, in which we learned a lot about what the universe entails, what its properties are, it is time to go to its infrastructure. The first manifestation of structure forming in the universe is known as the cosmic web. It's web-like features emerging from the primordial, yeah, even more, from the primordial mass distribution. And therefore, I would like to introduce the first speaker. I'm very happy to introduce the first speaker, Job Feldbrugge, who will be shining some light in terms of a new analytical model based on some very old work that goes back to the days of the Soviet Union, in fact, in terms of caustics and what they actually can do to describe the cosmic web. I'm very happy to introduce Job because Job is here from Groningen. He originally came from a small town nearby, Letterbert, and he studied here in Groningen mathematics, physics, and astronomy, majored in all of them, cum laude. After that, went on for a year to Cambridge to get his mathematics tripod before he started his PhD in Canada with Neil Turek at the Perimeter Institute. Last year, he decided to return to Europe, although the country where he went doesn't call itself Europe that much anymore. He went to the UK, to Edinburgh, which is the most European part of the UK. And there he is actually working at the Higgs Center as a fellow, and he is working on a wide range of subjects, going to the very first instances of the universe. That is another subject than what he will be talking about today, because today he's going to talk about the universe as it started off around 380,000 years into the Big Bang. And I'm therefore happy to give the floor to Job.
Thank you very much for inviting me to give this talk in this fantastic location. It's quite an experience for me to be in a planetarium. It's something I haven't done before. So I will talk a little bit about the cosmic web, which also featured in last day's conference talks by, for example, Henk Hoekstra. And I will take a little bit of a more mathematical perspective. So I will be talking about caustics in the cosmic web, and this is work in collaboration with Rien, but also Johan, who is here in the audience, Georg Wilding, who is at the moment not attending the conference, but he is abroad, Kevin Bixerman, who I believe is coming to the conference, Jihan Jan from Waterloo, Jonny, and Joost Veldbrugge, who is my father, and he did some of the drawings of our papers, and he is an actual collaborator. And I always have to mention that because otherwise people think I cite myself as my collaborator. So the cosmic web, can we please switch to the show, please? Yeah, great. So if we look back into the early universe, then it turns out that the complex universe we see today originated from something very simple. So this is a baby image of the universe. It's what we see if we look in radio all around us, on the whole dome around us, so the whole celestial sphere around us. If you look in radio and you look way back to the oldest light we can actually see, then you see this Gaussian pattern, which is an extremely simple statistical object. And it's kind of marvelous in large-scale structure that this gave rise to the cosmic web. So if we now switch to the Zeldovich approximation, then you will start from these Gaussian fluctuations, and you will see the emergence of a structure consisting of filaments, clusters, and walls. So here you see it starting to form. All the matter is clumping together, forming this web-like structure, where you have the mass moving along the streams guided by the cosmic web. So this is a purely analytical model of the universe based on only dark matter. And this is one of the models which we will be using in my subsequent analytic talk. So the important thing to notice is that this is really a three-dimensional structure, and there's loads of geometry coming to it. So I think this might not be the Zeldovich approximation after all. And in this case, it's the Illustre simulation, which is a simulation run recently on many supercomputers. And the key thing to take away is that you started from this very simple Gaussian object, and this led to this very complicated hierarchical, even nearly fractal-like structure, which we are trying to study in the cosmic web. And that's basically the purpose of our study. So if we can now switch back to my presentation. So this is a slice through this distribution. So this is the Millennium simulation. It's a little bit of an older simulation. But the important thing is that you see these empty regions, which are the voids. You see line-like regions, which can be either, in this case, in this slice, filaments, because they are lines, or they can be intersections of walls. And you have the clusters. And of course, we don't see dark matter. What we see is galaxies, but the galaxies are biased towards the high mass regions of the dark matter. So you also see a similar distribution in redshift surveys. So if we go to a redshift survey, and this is one of the triumphs of late time cosmology, you can take a telescope, you can point it at the sky, you can find galaxies, and by finding these galaxies, you can find the underlying structure. So in the upper two plots, you see the cosmic web in redshift surveys. So again, you see these empty voids, you see these filaments. And so in particular, universe not distributed on a regular grid, like Henk Hoekstra mentioned in his talk. And the purpose of this talk is trying to understand how this structure formed and whether we can develop a new perspective of understanding that. Because as Henk Hoekstra described yesterday, we have all these new telescopes coming up, like the Euclid's telescope. There's an enormous amount of data coming, but our theoretical understanding using analytic formulas is still limited, and mostly limited to Fourier analysis, which is of course great, but there's also a lot of geometric structure which you might miss if you don't try to develop new tools to actually probe this. So the upper left and the upper figures are observations, so real galaxies in our universe. It's our local backyard, whereas the other two red plots are embodied simulations, and you see that the same geometric structure arises, which is really promising. So caustics. What are caustics? Leo Koopmans described yesterday in his beautiful talk, lensing. And what you see is that in strong lensing, you can have an image which comes from two directions. So that's in geometric optics called a multi-image region. Caustics in large-scale structure are basically the same, but they are the three-dimensional version. And instead of working with a multi-image region, we will work with a multi-stream region. So what do you see in this plot? This is a two-dimensional embodied simulation coded by Johan. This is a Lagrangian fluid dynamic simulation, meaning that you trace all the mass elements, all the particles in the embodied simulation. You start with a homogeneous grid, and you see the development of multi-stream regions. For example, here, you see that three different streams overlap. And these streams are basically marking the place where gravitational collapse starts to kick in, where it starts to become nonlinear, and where structure forms. And in particular, you see this boundary. And this boundary is the boundary between the single or the triple stream region. And these are the caustics I will be talking about. Similarly, you see here around clusters that you have a boundary between a triple stream region and a 5-stream region. And so that boundary in this simulation marks the places where you go for even more highly nonlinear structure formation, where phase mixing starts to take place. And that's what we are trying to trace. So we're basically developing a mathematical formalism to track the geometry of the cosmic web through these multi-stream regions and caustics in real space. So to take this embodied simulation, you can just plot the multi-stream regions. So at very early times, you see that it's only a single stream region. The particles haven't had the time to move to actually overlap. However, a little bit of time later, you see that the first multi-stream regions form. For example, here you see this red feature, which is known as a Zeldovich pancake. This is the place where the first multi-stream regions are starting to emerge and particles are starting to overlap. Over time, these will grow, and they will form this fully connected cosmic web, which you can see here. And again, you see the red curves bounding the single to triple stream regions, and you see the red curves bounding the triple to 5 or 5 to 7, always an odd number, stream regions. And this is the basically incentive for this whole project. So caustics are not new. Caustics we know from optics and are studied for a long time. But in the 70s, there was a big breakthrough in caustic theory by Arnold and René Thom, who managed to classify them. So it's kind of miraculous, but if you take, for example, a swimming pool and you look at the light pattern at the bottom of the swimming pool, there are only a finite number of ways in which these light patterns can form. And these are classified by catastrophe theory. Soon after, Zeldovich, Arnold, and Sergei Shondarin, who feature on the lower right, wrote a series of papers trying to use this to understand the cosmic web. You have to imagine that embodied simulations at this time were still really primitive. So as far as I understand, the main objective was to develop a qualitative understanding of this cosmic web, of the structure at a larger scale, which was at that time, of course, still far into the future for us to observe. So in particular, they wrote a paper classifying the caustics in Lagrangian fluids. They described how they form in 1- and 2-dimensional models. But as you see, this is paper 1. Paper 2 was supposed to be the 3-dimensional cosmic web. However, for a long time, it remained at the 2-dimensional cosmic web due to some mathematical difficulties. However, recently, we managed to solve these difficulties, and this allows us now to push forward to the 3-dimensional cosmic web through caustics. And this in particular allows us to combine with embodied simulations. So nowadays, we have these beautiful embodied simulations. And we are trying to combine these caustics, which are basically from the ancient times of cosmic web theory, into the embodied simulations in order to see whether we can develop a new perspective of understanding the cosmic web, both in simulations and in redshift surveys. So how do these caustics work in practice? In Lagrangian fluid dynamics, you describe the motion of particles. It's nothing more than Newtonian dynamics. So what you do is you say the position of a particle Q, which started at this Q point, moves in time t to position x by being displaced by s. So this would be for an ordinary particle in Newtonian physics. The only difference is that we do it for all particles in space at the same time. And you look at the concurrence of these trajectories. What you can do is you can say, well, let all these mass elements conserve mass. So you basically squeeze a grid and you twist it, but you conserve mass, and particles might be turned inside out when they are going into a multi-stream region, but they always conserve mass. And for that reason, you can calculate the density by dividing the mass of the initial mass element divided by its volume. And now you can see that if you turn it inside out, the volume goes to 0 momentarily, and you get an infinite density. And this is the infinite lines, or the very bright lines you see at the bottom of your swimming pool, where you see these very bright caustics in optics. So mathematically, it looks like this. You have the density at a certain time, where you sum over all the initial positions which move to that particular point, and you divide by 1 over the determinant of the gradient of this X map. And in particular, if this determinant is 0, if this gradient, which is the deformation tensor, becomes singular, you find that you divide by 0, so you get an infinite contribution. And this you can see in the determinant of the gradients, or you can see it in terms of the eigenvalues of the gradient of the S function, the displacement function. And this is kind of important because in the subsequent talk, I will be always talking about both the eigenvalue, mu, which features in this expression. So if 1 plus mu is 0, you get an infinite density, and the eigenvector. The eigenvector is often ignored, but I will claim that this is actually a key ingredient to understanding the cosmic web through caustics. So it's very nice to see these infinite densities occur, but what is now the key ingredient which allows us to move from 2 to 3-dimensional cosmic web? And this is a theorem which we proved in 2019. And in retrospect, it's very elementary, but it took us a long time to figure this out. And I believe that if Arnold would have realized this small linear algebra problem, he would definitely have done it in 3D. So what you should imagine is that a Lagrangian fluid description is nothing more than a map from the initial positions to the final position space. So every point in this space, which is called Lagrangian space, which is the space of all the initial conditions, are uniquely mapped to a point in Eulerian space, which is the space of final positions. So if we look at the cosmic web, we look at this plot. But if we ask the question, where did the particles came from? Then that's in this plot. In particular, if you draw an arbitrary manifold in the initial condition space, so let's say this red curve C, you can map every point on that line to Eulerian space. You can just substitute every point with the point it would end up with. And then you get this red curve. And something special can happen in this mapping. Namely, you can develop a non-differentiable point. So whereas everything here is smooth, so a derivative exists, here you develop a singularity, very literally, because if you approach it from the left, from above or below, you get a different derivative. And this is the definition of a singularity. And what you now can prove is that this happens, this singularity happens for a point QS, if and only if this condition is true. So I won't go into the derivation of this condition. I can explain it in the break. However, the key point is that it is a combination of the eigenvalue fields. So you see 1 plus mu, which is exactly the same term we saw here, 1 plus mu. Oh. Yeah, so you get 1 plus mu. That can lead to an infinity. But you also see that the dual of the eigenvector comes in and the tangent vector. And the tangent vector is the tangent vector of this manifold at the point which you are studying. And this might look like a magical formula. However, you can basically derive it from linear algebra after you have taken your first classes at university. And if you now apply this formula, you can develop the Caustic conditions, which is a full set of algebraic conditions telling you when these Caustics occur and how they form. And in particular, we saw in the embodied simulation the fourth Caustic, which is the Caustic which you normally learn about. But there's a whole hierarchy of higher Caustics which also occur in optics, which we will study. So if you apply this simple condition to the whole of Lagrangian space, then you will find the fold condition, that's the A2 condition, which says that 1 plus mu is 0, which is exactly when the density becomes infinite. If you now apply this same Caustic condition to this manifold, then you end up with this condition. So you now see that you have the A2 condition, and in addition, you have that the eigenvector inner product with the gradient of the eigenvalue has to be 0. And if in addition to this first condition, the second condition occurs, you see that you develop this non-differentiable point in this curve. So what you should imagine is that at the first place of shell crossing, a sphere or a circle shell crosses. So this is the line which goes to infinite density, and that maps to Eulerian space to this shape. And you see there are these tips where it's non-differentiable. It's like a balloon you buy in a hospital, a get well balloon, where you always have a seam which is really sharp. And that's the cusp Caustic. And over time, this cusp Caustic will move and it will trace out a red line. And this line is the cusp manifold. If you now apply the cusp condition again, a Caustic condition to this cusp manifold, you get yet another Caustic condition, which is the swallowtail. And if you keep iterating this, you find all the Caustics. And it's actually a proof of Lagrangian catastrophe theory using elementary methods. And you get the whole classification. So all the Caustics you will ever see in the swimming pool or in the cosmic web stably are classified by these objects, which are completely described in the eigenvalues and the eigenvector fields. So it's very nice to have this understanding of the cosmic web in algebraic equations. But of course, we were talking about a geometric shape. And we were talking about filaments, clusters, and voids. So let's make a link to that too. So what you find is that if you look at the three-dimensional cosmic web, the A2 Caustics, the folds, correspond to collapsed regions, so that correspond to shell crossing at a certain time. You get the A3 Caustics, which are the cusps, which in 3D are the membranes. These are the walls in the cosmic web which bound the voids, the large empty regions which didn't shell cross. You get the A4, which are the swallowtail Caustics, which are filaments. So that's line-like structures in the cosmic web, which occur due to folding in phase space. You get butterfly Caustics, which are clusters. And in addition, you get a second branch, a second family of filaments and clusters, the D4 and the A5, the D4 and the D5, I mean, which is a second kind of filament and clusters with a different formation history, with different properties in the cosmic web. And this is a new realization. So how does this work in 3D? You start with a space, this is Lagrangian space, the initial condition space. You start with a universe without any shell crossing, without any multi-stream regions. Then it will start at a point, which is the A3 plus point. It's a dynamical point in the formation of the logical structure. And then it grows into a sphere, just like we saw the circle before. And if you now map that circle into Eulerian space, into the final condition space, then you get this balloon from the hospital. And this sharp ring is the cusp. And if you now trace this cusp over time, then you trace out a two-dimensional manifold, a sheet kind of thing, and that turns out to bound the empty voids. So besides the simple generation of a cusp, you can also see other dynamical features where the things interact. It's like a little bit like string theory, where you merge two strings, and you can get higher order caustics. And these all have different geometrical meaning. And we would expect that they also lead to a different local environment in the cosmic web, which will influence the star formation, will influence all the local properties of the cosmic web. So this way we are trying to bisect the cosmic web and turn it into pieces so that we can study it systematically, one by one. So this is all very nice, beautiful mathematics, but how do we actually use this? How can we turn this into something which is predictive? So the first thing to realize is that all these caustics don't rely on density, don't rely on the gravitational potential. The fundamental object of these caustics are the eigenvalues and the eigenvector fields. So if you take the upper left plot, that's a Gaussian random field. So see that as the CMB, the perturbations we saw in the sky. It's a Gaussian random field. It's kind of the simplest random stochastic function you can think of, completely described by its two-point correlation function or power spectrum. If you now take this gravitational potential or this density perturbation and calculate its corresponding gravitational potential, then you get this plot. Again, a Gaussian random field, which is slightly different power spectrum, but again, a very simple object. What you now can do is you can calculate the Hessian of the upper right figure, which is a second order derivative in X and Y. And this matrix, in this two-dimensional setting, it would be a 2x2 matrix, has, of course, eigenvalues and eigenvectors. And these eigenvalues and eigenvectors you can see on the lower two panels. And the surprising thing is that you start with this Gaussian random field, you go to this Gaussian random field, and you end up with this non-Gaussian field. So you started with a drop-like thing, and all of a sudden you see lines coming out. So if you ask your question, why don't we see a regular grid kind of cosmic web, but why see we see this filamentary network? That's ultimately due to the eigen equations and the eigenvalues. Because as I will show in a second, these lines are basically progenitors of the cosmic web we see today. So it's beautiful that using this very elementary mathematics, you can understand why the structure of the cosmic web is what it is today. It's one thing to run an embodied simulation and see that it matches. It's another thing to actually develop a mathematical understanding why such a thing happens. So this is the first observation. Don't forget the eigenvalue fields, and also don't forget the eigenvector fields, which are the red lines, which I'm not so sure where it's really clearly visible, but these are also highly correlated to this eigenvalue field, and together they give all the caustics. So what we can do is we can take the same embodied simulation I showed before, that's on the right. So this is a two-dimensional embodied simulation. And we can also do the Zeldovich approximation, which is basically saying the particles experience an initial gravitational potential, they get a push, they have a certain velocity, and they will never turn around. So on the left figure, it's the Zeldovich approximation. Initially, it's quite good. But of course, after the first shell crossing, it goes haywire. It's nothing like the right figure. And even though the Zeldovich approximation, which is normally only used for the early universe, is terrible at late times, to my surprise, it can still predict the caustics fairly well. So if we take the left figure, which is an analytical model, so don't need an embodied simulation for that, as a first step to understanding the cosmic web, which is in the right figure, I can calculate these caustics. So I can calculate the eigenvalues corresponding to that left figure. I can calculate the eigenvectors. I can calculate these algebraic equations, which we derived, and you obtain this network. So the background is the eigenvalue field. So you see all these lines. And then you see the red curves, which are the fault caustics, which are the places where shell crossing happens at a particular time. And then these regions are bisected by the blue curves. And the blue curves are the cusps. And in 2D, these correspond to the filaments. So if you now take all these lines and points, which are defined by the dynamics of the cosmic web, so tracing the dynamics of the deformation tensor, and you map it to Eulerian space, to an embodied simulation, you see that it's spot on. It's just on top. Everywhere where you would expect visually a filament, you see this blue line. So this basically illustrates that by tracing the dynamics of the embodied simulation or large structure formation, you can identify the key places where the cosmic web forms. So this is really a skeleton of the cosmic web. We don't predict at the moment the environment. We only predict where do you expect these structures to form. And in retrospect, it's not so surprising that Self-Bovic approximation works so well, because what we do is basically mark the places where nonlinear structure formation starts to take place. Using Zeldovic's approximation, you say, oh, that region is a void. I don't have to expect a filament or a cluster to form there. Whereas that region is starting to develop multistream regions and actually leads to structure formation. So we can do it in 2D. We can of course also do it in 3D. So this is a very small embodied simulation, and you see the time evolution where you see the cusp sheets and the filaments plotted in. And you see that at the initial time, you have a few isolated islands leading to structure formation, but soon they will connect up and form this full-fledged connected network, which you see in this lower right figure. And this is basically what we are after, because now we have a mathematical formalism of understanding the cosmic web without any additional parameters. So in 3D, it looks like this. And the key point to take away is that you have two different filaments which form at different geometric regions and have different formation history. The one forms early, the other one forms later. The one is thin, the other one is thick. So we are currently in the process of fleshing out all these details. So this is basically the whole framework. And we hope that this will lead to different ways of understanding the cosmic web and developing new probes to actually study redshift surveys. So one thing we have been doing is with Georg Wheeling for his PhD thesis, we have been tracing the caustics on an embodied simulation. So no Zeldovich approximation, just the numerics of the embodied simulation, and try to flesh out the caustics and their dynamics, in particular topology. So what you see here is the caustics at different times, as we did before. And this is the determinant of the gradient of the X map. And what you see is the zero curves here match indeed on top of these curves. But what you see that at late times, the resolution is not good enough and you get a lot of jitter. However, if you trace only the boundary between the single and the triple stream region, by looking for every mass element at the first crossing of this determinant, you can build this map, which is a complete summary of the evolution of the boundary between the single to the triple stream region. And you can see that the super level set, so the isocontours of this plot, correspond basically to the history of the boundary between the cosmic web. So here you see that only the single to triple stream region receive a red curve, because these are computed from this plot and not from this whole mess. And what we now can do is we can trace the evolution of the cosmic web through these maps. And so this is completely based on an embodied simulation, where you can calculate this new field, calculate its critical points, and you see that the whole formation history is described here. So you see that initially there are no multi-stream regions. Here you see the first few multi-stream regions form, corresponding to these islands, which are Zeldovich pancakes. And at the place where these merge at a saddle point, they merge also in Eulerian space. So in particular, the topology of the upper plot is the same as the topology of the multi-stream regions in the lower plot. And we've been using this to study the embodied simulation. So again, here you see the new fields which describe the single to triple stream regions in the embodied simulation. Here you see the Zeldovich approximation which correspond to it, which is of course different, certainly at late times. However, the key structures are the same. So for example, here you see these three maxima, which correspond to these three maxima. So we are trying to see how you can analytically describe the topology of the embodied simulation using these techniques. And finally, as a takeaway, we are trying to develop qualitative tools to actually probe this. So it's one thing to identify these structures. It's another to quantify it and hopefully in the future compare the predictions with real observations. So we do this with so-called persistence topology. And what you basically do is you trace the evolution, how the topology changes over time. So if you take the lower left plot, and you see that you first generate an island using a maximum. And here you see a second island being generated. Here you see a third island being generated. And these are births of different structures. But here something amazing happens. This one joins with this one through this saddle point. So there's a bridge connecting the two. And this means that one of these two structures is basically killed. And what the rule is, you kill the shortest lived feature. So the oldest one survives. And what you can do is you can say, well, this feature was born here. It dies there. It gives you a coordinate because you have a birth time and death, time of death. And that can be seen as a point in this diagram. So you can basically take the topology of the superlevel set, and the persistence diagram, which is this diagram, is a kind of a fingerprint of it. If you now do that for the embodied simulation and the Zeldovich approximation, then you obtain these kind of figures. So the point distribution in these two figures give you a fingerprint of the hierarchical nature of structure formation during its dynamics, which is something new. It hasn't been done before. People normally study the density fields. Here we study evolution. You can also look at the number of islands, voids over time, which you can see in these plots, which are known as the Betti numbers. So you can use this whole mathematical formalism to quantify what we see in these embodied simulations or analytic approximations. I think I'm nearly out of time, Rien. So let's finish now and say that the caustic conditions allow you to develop a mathematical understanding of the cosmic web, and in particular its dynamics, which is unavailable without this formalism. And my hope is that this will give a new perspective to probe both analytic and numerical structure formation. It's fully general. It works also for other dynamical systems. This theory predicts two different kinds of filaments, whereas we normally are aware of only one. And this is due to the eigenvector fields. Finally, we are now working on developing constraint techniques to basically calculate how the structure formation works systematically. And this will ultimately lead to a pipeline using machine learning, which we would like to apply to the redshift surface. This is still in the future, but I think this is getting closer with every day. So thank you very much. And I'm willing to take questions now or later today.
Okay. I already see two hands raised. That was number one.
Extremely interesting. Thank you very much. So I have several questions. The first one has to do with initial conditions. Now you assume Gaussian initial conditions. We know quantum diffusion during inflation produces exponential tails at large values of density contrast. So what would you expect that this would do to your structure?
So we haven't actually studied that, but the whole formalism is not relying on the Gaussianity. So you could, in principle, just generate such an initial random field and see what happens.
Would just speed up the way you transfer from the, say, Zeldovich to the full embodied?
It could be, but it of course depends on the details of the deviation from Gaussianity. But for example, Neil Dalal has proven in a paper that if you have small non-Gaussianities in the initial conditions, which might be able to observe in the CB, it might lead to accelerated structure formation in peaks. And this is something you would be capturing with this. So this is more like a visualization technique or a new perspective of understanding the cosmic web than a real physics theory, as in particle physics.
So I have a second question. It has to do with this duality between the density field and the fractal dimension field. So if you could look at the structure in the cosmic web, you could characterize by filaments, so one-dimensional, clusters, zero-dimensional, voids, three-dimensional, sheets, two-dimensional. So this mapping one-to-one must be related to those Betti numbers that you were describing, to the topology.
Sure.
So could we have a different description of the logical structure in terms of simply these fractal dimensions distributed in space? So rather than having the spatial description, you would have the fractal dimension description.
So I haven't really worked on that, but Bernard Jones has a rich history in fractal power spectra. So he would be the guy to ask in this case.
Thank you.
But I believe that that's all related and it can be done, but we only fleshed these mathematical details out recently. There are all kinds of numerical problems to solve. So we have been busy with doing. So
my impression is that from your initial conditions, you already could get this
sure.
dimension.
I agree. It's early.
Thanks.
Okay, let's have one more question. I saw Seth Lloyd had a question.
First of all, thank you for blowing my mind. Not just with the simulations in the planetarium, which were great, but really this is the first time that I feel momentarily that I understand the structure of walls and filaments and voids. I have a question about the persistent homology and the calculation of the Betty numbers. It went by a little fast for me. So in the persistent homology, are you normally you have a grouping scale that, and then you look at the topology at different grouping scales and calculate at the number of holes and voids, et cetera, and connected components, which are the Betty numbers. But somehow it looked as if you were calculating them in time rather than in length scales. Are you calculating them in length scales or in temporal scales?
In this case, it's in time, and that's the first time this is done. So it's indeed different from what you would normally perceive. But you could imagine that a feature is born, but is assumed very rapidly in a bigger structure in time. And that would lead to a point which would be very close to this diagonal, which we say it has low persistence. It only lasts a very short time. So indeed, you could do this at different scalings. So you could do this for fine grained initial conditions or smoothed initial conditions, and then you basically add yet another dimension. So you could have basically a family of persistence diagrams where you see the persistence diagrams in time, like you described, but then for different spatial lengths.
I see. So the latter would actually give you the space-time topology as opposed to merely the temporal topology that you're looking at.
Indeed.
There. Okay, thank you. That's great.
Okay, one final short question, Jan Tran.